All right, so the title of the talk is, it's kind of optimally vague because at the time I had a kind of a general idea. But basically I'll start this talk off with kind of a story. So last January I got invited to California. There was this workshop that HP hosted, and there were all these really knowledgeable people in R core, and I got invited also, which was awesome. And the whole goal for this was the goal was to standardize the API for exposing distributed computing in R, learn from the experiences of attendees, and using R for large-scale analysis, and collaborate in open source. And in that sense, the whole workshop was like a failure, right? I mean, yes, and most of the reason for this is that you have a lot of people that are really working in diverse areas of distributed computing and programming with data. Like for example, you have George Osterkoff, who's at ORNL, and he's really interested in really large-scale linear algebra. Or you have like Simon Urbanek at AT&T, where they're dealing with petabytes of data that they want to be processing. But they're actually doing these really, they're coming at, their approaches are really different, partially because what they really want to, the end tasks, the thing that they want to accomplish is actually very different. Yeah, I think I was probably invited because right now I kind of corner the market on CRAN packages that start with big, right? So big memory, big analytics. But anyway, so the idea was, so in that sense, we didn't quite meet the objective, but it was really informative. And so for this talk, I decided I would kind of take a step back, and I've done a fair amount of collaboration for and with groups. So one of the things I wanted to do at this point was just kind of summarize what are kind of not software APIs that I'm constantly using, but basically what are these general principles that allow me to get to the analyses that I'm interested in. So there are only 3 of them, and I've got 15 minutes and 57 seconds to go through them. So I'm going to actually kind of outline those and show them, try to show you how they're relevant. So that's what this talk's about. So the first one, and I kind of tried to prioritize them by importance. So one of the most important for me is that most of the time when I'm working on these problems, I need to think about how to scale them. One of these, the first principle is that compute cycles are cheaper than brain cycles, right? So this is a really big deal, because when I'm spending time trying to, so all right, so let me just go to the next slide. Jared will like this. So along with R and Python, I'm a C++ programmer, and there's this Scott Meyer's new book came out recently, and he says, because you're a C++ programmer, there's an above average chance you're a performance freak. If you're not, you're still probably sympathetic to their point of view. If you're not at all interested in performance, shouldn't you be in the Python room down the hall? So I do program in Python quite a bit, and I was thinking, well, this is one perspective, and for most of the stuff that I'm doing, it's wrong, because a lot of the times I'm trying to get at an analysis. I'm not trying to optimize. I'm not necessarily trying to optimize it, because a lot of what I'm doing is trying things, see if they work. If they do work, I'll assess whether or not they're fast enough. If they don't, I'll move on to something else. So basically, the other side of this is that performance freaks value task execution time over their free time, right? So sometimes it's very important to get things optimized and going as fast as it can, as fast as you can. If you're actually trying to understand structure within data, a lot of times that's not the case. And it's really easy to get sidetracked with a lot of these different ways that people are optimizing things, but a lot of times, if that's not your task, you shouldn't worry about it, and you shouldn't spend a tremendous amount of time on it. The other thing now, and this is a much bigger point now than it was 10 or 15 years ago. horizontal scalability beats vertical scalability when compute is a commodity. So by horizontal scalability, I mean if I can define a task and I can get and I can make it faster by spinning up a whole bunch of, by using more CPUs, that's a much better solution, or that's a much quicker solution most of the time than going to Amazon and buying a book on OpenCL and trying to figure out how to get a GPU to run things more quickly. And again, to this point, it's when performing an analysis, brain cycles are better spent on analysis and not implementation. I guess one example is big memory. So I first started writing big memory, it was actually for Netflix, right? Because I didn't have a machine, or my home machine wasn't big enough to handle the entire Netflix data set as a data frame in R, and I knew about memory mapping, and I said, well, I can just do this memory mapping thing. And 4 years later, I have a PhD, but I didn't really do anything with Netflix after that. So you have to be really careful if you're gonna, focus. So I totally dropped the analysis and spent all the time on the implementation. Now, luckily, the implementation became my job because my goal at the time was to get a PhD. I guess Netflix would have been cool too, but it's. I think a lot of times in analysis, it's very important to be able to distinguish these two things. So how do you actually do this? So I use for each a lot, and if you haven't looked at for if you haven't looked at for each, you should, especially if you're thinking about needing to scale things. And it's basically, the whole idea is that I can write one of these things that look like a loop. And it's going to be, so for each, I do a lot of things with iterators. So I don't usually use DD or plyr because I don't usually split things into partitions. So if you do any kind of signal processing, a lot of times you're thinking about doing things like convolutions, and you have these overlapping windows. So because I'm not partitioning, I'm usually using iterators, which is a great package that actually the R community copied off of Python, right? Steve Weston, who wrote that, is unabashed about saying, yes, I just took this from Python. So, so they took data frames, we took iterators. But the idea is you write this loop, each one of the, and you process whatever you're iterating over. And this code right here will run on single machine, single processor, single machine, multiple processors. It'll run across. It'll run in the cloud. If you talk to Brian Lewis, he'll tell you how to do these loops in an elastic way, where you can actually be you can create new workers that'll do jobs. So just this piece of code lets me kind of scale out about as much as I really want to or need to. Just for the sake of completeness, if your challenge isn't embarrassingly parallel, get a bigger machine. This is kind of this is a little bit heavy-handed on my part, and somebody challenged me on this a little while ago, and so if somebody wants to challenge me, I have this. So this is actually this is the biggest machine I have access to right now. So this one has over 4,000 cores and a quarter petabyte of memory. So I mean, not everyone can do this. And maybe if you go to ORNL and you say I need compute cycles, especially if you have a university affiliation, they will give this to you. But a lot of times for some of these tricky problems, sometimes it is just better to throw more hardware at things. And the other thing you can do, I mean, Brian hasn't been mentioned for, I guess, 2 talks now. So I just want to mention the other thing you can do is talk to Brian Lewis, because he knows a lot about these types of problems. All right. The next step. The next step is that data exploration is critical, especially for me, because a lot of times I'm switching domains. I don't usually have a lot of intuition about what data look like or should look like. And so, most of the time what I'm doing is with graphs. Now, or with visualizations. Now, if you think about, as you get more and more data, this becomes, sorry. I should first, why graphs, or why visualizations? And I actually like visualizations over models. I'll usually wait as long as possible to actually fit my models. And part of the reason is, when we look at visualizations and we discover things from visualizations, we're actually using, we're using the human visual system, which has been evolving for like at least millions of years now to be optimized to be able to look for, to find patterns. I think most machine learning is only, like linear regression goes back to Gauss, so it's not nearly as old. So then the next issue is how do you actually scale these explorations? And there's been a lot of work in this area lately, and usually what we're doing in the end is we have to organize data, right? We have a lot of data, either abundance or variety, and we need some way to be able to manage this and be able to look at it and be able to find something interesting in it. And so I would say that the two approaches that people use right now is they organize data by resolution, right? So this would be like if you're looking at map data, and you have summaries of census blocks, and you have heat map using the census blocks, and then you can zoom out and you see things by country level, right? So this is organization by resolution. The other one is division. So you end up dividing the data up somehow, and you create a lot of visualizations. Now, in both cases, you're essentially managing the complexity and abundance with interactivity, right? It's either, in the case of the map data, you have the interactivity that gets you to, from country to census block to whatever. In the case of division, you're creating a lot of these different visualizations, and you actually need a way to, you need a little bit more organization. So this has actually been interesting me a lot lately, and it's one of those things where, so if you talk to people that did a lot of computing and linear algebra in like the 80s, those guys know everything. And this is actually another good example, and this may be kind of pre-80s. This is the idea of a cognostic. So if I generate a tremendous number of graphs, I need some way to be able to navigate them, right? So John Tukey at AT&T Labs proposed this idea of a cognostic. Now, if you've ever gone to JSM, there's always like this group of people that talk about cognostics, and I never knew what those were, and like they had their own language that I didn't understand. But basically, a cognostic is some quantitative summary that's associated with a visualization, and they call the visualizations displays. So the example I have is so there's this R package called Trelliscope that actually handles cognostics. So this is data derived from, it's from the Bill and Melinda Gates Foundation. They were really interested in growth trajectories for children at a young age. So with this, I have a set of cognostics, and one of them is number of points. So in this case, so this is the number of points on each one of these visualizations. And I should have said that this visualization is this is measurements for an infant for their growth trajectory, and this is the lowest smooth curve. So this is an individual. This is how their BMI is changing over time. So the types of things I can do is I can filter by the number of points. Maybe I'm only interested in the ones with the most points. I can do things like the size of the mean residuals. So let me get the ones with the really big residuals compared to the lowest score. And I've whittled down from over 8,000 visualizations to 12 that I may be really interested in. And the way I did that, again, is because I had these associated measurements with each one of these with each one of these visualizations. So the size of the residuals and the number of data points for this. And I was quickly able to get to a set of visualizations that I may be very interested in. So that package is called Trelliscope. It was written by Ryan Hafen. He knows JavaScript, so we don't have to. All that was written in R. The other thing I really like about it is that because I'm doing I'm working with investigators a lot of times, I want to be able to provide them with digital artifacts that they can actually download and look at themselves. The other thing is there's this thing to avoid if you're dealing with investigators where they look at a result and they say, well, this looks good, but now I want you to change this. And this looks okay, now I want you to change this. So with this, you could potentially provide somebody with an environment where they're able to do the exploration themselves. So they can answer their own questions, and you don't have to deal with that cycle of going back and forth. All right, the third point, I'm on time, is there's still no panacea, and so I'm not just being, it's not quite a platitude, but so neural networks, or convolutional neural networks, like they're called now, they've been really interesting, I think, for people to see, for us to see, especially if we remember when they were just called neural networks, right? Because there's this new twist on them, and they found ways to make them fail in these new and spectacular ways. And one example is there's a paper. Actually, there's a website in this paper by Goodfellow where he takes this picture of a panda, and the neural network it's all right, 57.7. That's pretty sure it's a panda. And then they add this noise to it, right? So it's if you look at it, it's high frequency noise. But for some reason, when you add these two things together, the neural network says this is almost absolutely a given, right? So, and just because this was an entertaining example, there's actually a couple more, right? So you can go even further with this. So this is a king penguin. This is a starfish. These look like things from like the 60s to me, right? We have neural networks on acid right now. And now, the thing with neural networks and convolutional neural networks is they provide this thing everyone's wanted. It's a lie everyone wants to believe, right? And that's that you don't need to do feature extraction. And that's why people keep going back to these, right? I can take basically the idea is I can take a whole bunch of images, I can set up neurons or whatever to point to each one of these pixels, I can push it through a whole bunch of GPUs, and I get results like this is a king penguin. Now, most of the time, actually, they do really well. And to be fair, this is a special type of noise that you need to add to be able to get this. It's called adversarial noise. And and I was thinking about, I get most of my images either I take them or I get them off the internet. Nobody is adversarial on the internet, so maybe this is a solved problem, right? But neural networks were kind of supposed to be this panacea for doing classification, and in some sense they've actually done a really good job. But if you look at that's not a very broad context, right? We're doing object detection for consumer images usually with some processing. So basically, so it's not really a panacea. And what it reinforces is that working on a variety of different problems still requires a variety of different tools and approaches. Now, as our users, we have really it's really nice that we have GitHub and CRAN. We have the ability to leverage what other people know, but in the end, a lot of what we're doing is we still have to understand, take the time to actually understand the domain, perform the analyses, and then also interpret the results and actually add to the narrative, which I think was a really good point made this morning. Because in the end, that's what the people that we're collaborating really want, is for us to contribute and help contribute to the narrative that they're writing for the data. That's it. I'm out of time. Thanks.